When analyzing the marble machine, one can regard it as a system of multiple masses, each bearing a rotational kinetic energy equal to 1/2 of its moment of inertia, I, times the square of its angular velocity, omega. The angular velocity, that is, the rotational speed, only changes when the energy changes. Changes in energy are caused by positive sources of power, such as the user's pedaling, and negative sources, such as friction or the load of lifting marbles. The system is thus tight when for the same change in energy, there is a smaller corresponding change in the speed. This video will explain why it is much more difficult to achieve this definition of tightness using the current Huygens Drive with Gramophone Governor than with my proposed derivative Well CVT Controller. I will first go over how each of these three designs achieves this tightness and will then provide graphical visualizations of each of their performances. The first design simply couples the machine to a flywheel via some fixed gear ratio. The machine, in this case mainly the programming wheels, possesses a moment of inertia I, but is geared to rotate fairly slowly. Hence, it will have a smaller rotational energy at its given speed. This means that for the same change in the system's energy due to the input and load, its speed will change by a greater amount. When we add a flywheel, we give it a large moment of inertia and gear it up to rotate much faster, contributing a much larger rotational energy to the system. Thus, that same change in system energy will incur a smaller change in the system's speed, which makes it tighter. Next, we have the Huygens Drive with Gramophone Governor, which is your current design. Instead of allowing the input fluctuations to act directly on the entire machine, the machine is insulated from them by this mechanism. These input fluctuations first go through a small flywheel and then into the Huygens Drive as shown. As you may already know, due to how pulleys work, a portion of the changing input forces will make their way to the output through the tension in the chain. Here we have an analysis of the Huygens Drive's performance. The details are shown for reference, but what is important is the outcome. This analysis assumes the input and output sprockets to have the same radius r, that the input and output sprockets are coupled to moments of inertia I1 and I2, that the tension contributed by the Huygens weight's mass is completely cancelled out by the input and load at all times, and that the auxiliary tensioning weight is negligible. Fv represents the varying force applied at the input. This causes a torque, and hence a rotational acceleration on the input sprocket and a tension on the chain. That tension pulls a Huygens weight upward and applies a torque accelerating the output sprocket. Due to mechanical advantage, the sum of the downward movement of the left side of the chain and the upward movement of the right side of the chain equals half of the upward movement of the Huygens weight, as shown by this equation. Knowing this, we can solve the equations to yield the force Fi acting on the output in terms of the force Fv applied at the input. This function looks like so, where for a mass of 0, we start with a force of 0 and increasing it approaches a constant value. Interpreting this, as you increase a Huygens weight's mass, m, toward infinity, the output force equals a ratio of the input force that depends on the moments of inertia of the input and output. This means that the ability of the Huygens Drive to filter out input fluctuations decreases as m increases. This is because the work the mass can do, that is, the energy it can put into the system, is equal to the applied force times the distance over which it is applied. If the mass is very heavy, then it will barely move, and thus cannot do much work to absorb the input surpluses or to fill in input deficits. If we decrease m, then the force on the output decreases towards 0, implying that the Huygens weight is light enough to be dynamically raised and lowered to maximally filter the input fluctuations. The problem is that said weight would have to oscillate vertically by a large amount, counter to the purpose of your current tightness meter, and would not be able to counteract the output load. And as the output load increases, we require a larger mass, which as shown, causes said output to see more of the input fluctuations. Alternatively, if you make the inertia of the input much larger than that of the output for some Huygens weight mass, then the force seen at the output will approach 0 because the input would barely be accelerating from the input force. Likewise, if the output's moment of inertia is much greater than the input, then it will come to see the entirety of the input fluctuations. The Huygens Drive is simply not a very good way to filter an input, and it is arguably being misapplied. The Huygens Drive was originally designed to have the input sprocket locked most of the time, while the tension from the mass drives a constant load of a clock escapement, the force disturbance from lifting the weight only happening every few days. Since the mass is allowed to fall, it is allowed to apply a constant force over a distance and hence do work. In your design, we try to keep the mass's position constant, so it does not move and thus cannot do any work toward maintaining the machine's speed. Therefore, almost all of the work is being done by the user, while the only work the mass can do is to slightly filter the input fluctuations. So you can now see that practically, both the constant power input level set by the Huygens weight and a portion of the input fluctuations will make their way into the Gramophone Governor. The governor can be said to measure the speed of the driveshaft, using this to move a brake disc to generate a negative power from friction which it draws away from the system's energy. So if there's a net power changing the energy in the system, the gramophone brake will change its pressure and hence the negative power it applies until the net power becomes zero, leading to an equilibrium where the driveshaft speed remains constant. The problem is that if the machine's power consumption changes, then so will the equilibrium speed. That equilibrium speed can change by a decent amount for not much of a change in power. To explain this, I first use a diagram like so, with links, flyweights, a spring, a brake disc, and a brake pad. As the governor rotates at a certain speed, the flyweight M is pulled outward with a force proportional to that speed, which through the tension in the link pulls the sleeve and hence the brake disc toward the brake pad. The spring helps control at what speed the brake starts contacting. Once in contact, increasing the speed increases the contact force and hence the friction applied. And when you do the geometric analysis, you see that said force increases with the square of the speed. This force can be plotted as a portion of a quadratic function depending on at what position the brake starts engaging. That engagement position is represented by the dashed red line, while the solid black line represents a maximum displacement of the governor's sleeve. This force on the y-axis increases at an increasing rate as opposed to a constant rate as the speed on the x-axis increases. When you apply this force of friction from a certain radius while the disc is rotating at a certain speed, multiplying the resulting torque by that speed calculates the power dissipated by the brake. So if the gramophone governor is currently dissipating this much power, then if the system's net power increases by this amount, the speed will increase, causing the gramophone governor's dissipated power to increase until the net power is zero, again at some equilibrium speed, the reverse happening for a decrease in net power. As such, we can define tightness as having a smaller change in the equilibrium speed for the same change in system power, meaning that this curve needs to be steeper. This can be achieved by increasing the strength of the spring, by increasing the mass of the flyweights, but only by so much, by increasing the brake's coefficient of friction, by making the governor longer, or by engaging the brake at a lower speed relative to the governor's maximum. So to increase the tightness of the machine, you must either minimize the fluctuation of its power consumption, or you must increase the size of its flywheel so as to average out the changes in speed resulting from those fluctuations, or you must operate the gramophone governor such that its friction steeply increases or decreases for changes in speed, which would be rather inefficient. As for why this design appears to work, it is because of the lack of a changing load and the efficacy of the visual feedback provided by the Huygens weight, not due to the design's resilience against changes in system energy. It would have probably worked just as well for a constant load if you were to have bypassed the Huygens Drive, removed the gramophone brake, and just adapted your input to keep the governor's sleeve at the same position. We thus arrive upon my derivative Well CVT Controller design, which can handle almost any fluctuation in the input power and the system's load. This design places a wheel and disc CVT or equivalent between the input and the flywheel and uses a centrifugal tachometer to measure the speed of the drive shaft in order to control the horizontal position of this control wheel to set the gear ratio from 0 to infinity. Thus, if there is an energy surplus in the system, the tachometer will detect the resulting acceleration and increase the gear ratio to absorb that energy into the flywheel. Likewise, if there is an energy deficit, the tachometer will detect the corresponding deceleration and decrease the gear ratio in order to put that energy from that flywheel back into the system to maintain the speed. Given that, due to the way the CVT is set up, it is virtually impossible to exceed the target speed by a certain percentage because the flywheel would be able to absorb that energy almost indefinitely. Likewise, it would require a dissipation of the entire energy of this flywheel in order to decrease the speed by the same percentage below the target. I will now present the performance of these designs visually using graphs. In this model, I am assuming programming wheels of a combined width of 3 meters, a diameter of 1 meter, and a thickness of 3 centimeters. Then for the flywheel, I am assuming it is annular in shape to maximize the moment of inertia, has a diameter of 2.5 meters, and happens to be mainly constructed from foam so as to weigh only 25.5 kilograms. The horizontal scale is measured in RPM, but due to limitations with the Desmos graphing calculator, I have set it so that 0.6 represents our target speed of 60 RPM as shown by the vertical dashed green line. For the vertical scale, this is measured in kilojoules, so as with this horizontal dashed green line representing the system's total rotational kinetic energy at the target speed, 0.788 as seen on the right side of this coordinate corresponds with 788 joules. The purple graph plots the total energy in the system with respect to the speed of the driveshaft for the case where the flywheel has a 1-to-1 fixed gear ratio with the driveshaft, and the driveshaft has a 60-to-1 gear ratio with the programming wheels. This total energy is calculated using the previously shown equation of 1/2 I omega squared, where I is the moment of inertia of the programming wheels and the flywheel in this case being made to have 10 times the moment of inertia of the programming wheels, and the angular velocities, omega, are such that the programming wheel rotates 60 times slower than the driveshaft and flywheel. So if the machine accumulates an excess of around 100 joules, then that would increase the speed from 60 rpm, as seen on the left of the coordinate, to almost 64 rpm. Likewise, if it were to instead lose 100 joules, then the speed would decrease to around 56 rpm. If you make the flywheel heavier, then the curve will increase more steeply, and the speed for the same change in energy will have changed by less. The Huygens Drive and Gramophone Governor approach is excluded from this particular visualization since it is very difficult to analyze the energy in terms of speed when the dissipated power depends on said speed. You can refer to the earlier section covering the Gramophone Governor for plotting of dissipated power versus speed. The green curve shows the exact same plot of energy versus driveshaft speed, but for the exact same flywheel being connected to the driveshaft using a CVT. So imagine taking this governor design and using the position of this sleeve to measure the current speed of the driveshaft. That is, to operate it as a tachometer. Then imagine using the position of this sleeve to set the position of a control wheel, over here, to set the gear ratio between these upper and lower CVT discs. That connection implies that if the driveshaft speed decreases by a certain percentage, then this control wheel will move such that the gear ratio will decrease towards 0. Likewise, if the driveshaft speed increases by that same percentage, then the control wheel will move toward the gear ratio of infinity. Those lower and upper percentage bounds on the driveshaft speed are represented by these two vertical solid green lines. So as we decrease the driveshaft speed toward the lower bound, the gear ratio between the flywheel and the driveshaft likewise decreases towards 0, decreasing the flywheel speed and hence steeply decreasing the system's total energy. We only reach the lower bound on the speed once the flywheel has come to a complete stop, after which there will be nothing left to absorb the energy losses to the programming wheel's rotation. Likewise, as we increase the driveshaft speed toward the upper bound, the gear ratio increases toward infinity. That causes the flywheel to go ever faster and faster, absorbing the excess energy effectively indefinitely, so long as the CVT does not slip and the mechanism does not fly apart. If so, the driveshaft speed will never ever exceed the upper bound. So if we take our definition of system tightness as being a smaller change in driveshaft speed for the same change in system energy, then clearly this design with a CVT is substantially tighter than the plain flywheel design where the flywheel has the exact same moment of inertia. And if you thought that performance was impressive, notice that I've set these bounds to be 50% of the total 120 RPM range of the tachometer in this model. So what happens if I lower that range to just 1%? As you can see, the energy curve just gets steeper and steeper until it's basically a vertical line. So if I were to sample a part of that curve, you would see that for the same change in energy, the change in the driveshaft speed, as seen on the left of that coordinate, is absolutely minuscule. But to achieve this incredible performance, we need to be able to change the gear ratio by a much greater amount for the same change in speed. So let's say that for these CVT discs, we have a range of 15 centimeters to get from a gear ratio of 0 to infinity. Likewise, let's say that to measure an increase in speed from 0 RPM to 120 RPM, the tachometer's sleeve must move from 0 centimeters to 50 centimeters. So to achieve that 1% tolerance range, we would have to take 1% of the tachometer's 50 centimeter motion range, in this case 5 millimeters, and multiply that upwards into 15 centimeters of motion of the control wheel. So that would be a 30 times motion gain. That much motion amplification would require a lot of force, which can be supplied by the torque amplifier that I described in my original video. One thing to note is that there are actually other ways to arrange a wheel and disc CVT. So instead of having two discs sandwiching the control wheel, we can have just a lower CVT disc with the control wheel connected to the flywheel, or we can have it the other way around. So in this case, we are only controlling the lower bound of the speed using this disc, while here, we are only controlling the upper bound. The latter I have represented with this red graph, where it, like the green graph, prevents surpassing of the upper bound, but on the other hand, allows the drive shaft to slow down below the lower bound while the flywheel is still in motion. As you can see, it still performs a lot better than keeping the same flywheel's gear ratio fixed, but does not perform as well as using two CVT discs to control both the upper and lower bounds. Mind that sandwiching of the control wheel may enable greater traction. Now what if we want to see how the driveshaft speed varies as we vary the energy in the system with respect to time? In the case of the flywheel with fixed gear ratio, it is easy to solve for the driveshaft speed, omega ds, in terms of the system's energy using algebra. But for the green curve, the flywheel's speed is related to the driveshaft speed in a more complicated way that makes it very hard to solve for said driveshaft speed. Fortunately, I was able to approximate it with this blue curve, allowing me to produce these plots. Now we can see how the values change with respect to time. First, we have the total energy in the system indicated by this orange curve. It starts off at around 788 joules, indicated by the dashed orange line, and is changing with a pedaling input. Here, I'm assuming that pedaling input is trying to achieve an average input of 75 watts, with 2 strokes, one for each leg, per second, such countering a constant 75 watt load from the machine. Then, we have the driveshaft speed as a result of that changing system energy, the initial and target speed being shown by the green dashed line. The purple curve is for the case of the flywheel with fixed gear ratio, whereby the speed fluctuates rather much. The Huygens Drive can be simulated by reducing the energy fluctuations since those are being absorbed by the Huygens weight by a certain amount. See the earlier section of the video for details on why it isn't very good at doing that. Lower energy fluctuations means lower fluctuations in the driveshaft speed. Again, it is not practical to simulate the Gramophone Governor using this method. Finally, we have this green curve corresponding to my CVT design, which is doing such a better job that I had to increase the tolerance bounds, shown by these horizontal solid green lines, to 50% of the maximum tachometer range so you could see it changing. The blue curve shows the speed of the CVT-coupled flywheel as it absorbs the energy changes to minimize the changes in the driveshaft speed. Likewise, if I were to increase the energy fluctuation, which could be due to either the input or the system load, to something ridiculous, such that the flywheel almost comes to a complete stop, as you can see, the fixed gear ratio design is having a very hard time, while the CVT design remains well within the percentage bounds. Here, since the flywheel's energy is almost completely depleted at the energy lows, we can see distortions to the driveshaft speed curve, illustrating that this design is necessarily worse at compensating for energy deficits than it is at absorbing energy surpluses, but it still does so much better than the fixed gear ratio flywheel. If we increase the motion gain between the tachometer and the control wheel so that the gear ratio changes more for the same change in speed, we can bring this tolerance bound down to just 1% of the total 120 RPM tachometer range, yielding exceptional tightness in the face of this immense fluctuation in system energy. Finally, if we were to remove the pedaling input and maintain the 75 watts of power consumption, then the fixed gear flywheel and hence the drive shaft would come to a stop within 10.5 seconds. The CVT-coupled flywheel would also come to a stop in that time, but would have throughout transferred energy into the programming wheel to keep the drive shaft from slowing down below the lower bound. Note that the area to the right of this is not valid for the simulation. Alright, I hope this presentation has made it much clearer why this new design is so much better at keeping timing than this original design. Thus, what we need to do is to determine what the expected energy fluctuations of the actual marble machine will be, and from that determine whether or not something with this kind of performance is actually necessary. And if we do wish to construct this CVT design, all of the practical considerations as well as details on this usability for the musician are covered in the video shown.